Cubics. The general expansion of a perfect cube, which you may or may not have seen before. So a cubed plus 3a squared b, 3ab squared b cubed. It's a lovely symmetric pattern, as all expansions turn out to be, in that the power starts at 3 with the a and it works its way down. The power of b builds itself up, but you'll notice the coefficients are lovely and symmetric as well. 1, 3, 3, 1. When it's a minus b all cubed, very similar pattern, but the signs alternate. So we start with positive, we go negative, positive, negative. Okay. Difference of two cubes. Okay, we have a difference of two squares formula. We also have a difference of two cubes. Just like difference of two squares, it starts off a minus b. But in the second one, again, you'll notice this pattern of a starts with squared, so the next power down, but then the powers of a go down by 1, so in the second term it's a to the power of 1, third term it's a to the power of 0, so we don't actually write it down because that of course is 1, and the powers of b go up by 1. Any particular term there, if you add the two powers together, you should get 2. Okay? Now we don't have a sum of two squares formula, but we do have a sum of two cubes. So this one, a cubed plus b cubed, starts off with a plus b. And then the second one, it's a squared minus ab plus b squared. So very similar formulas. Basically, you start with whatever the question is. So if it's a minus, we start with the minus. If it's a plus, we start with the plus. And then in the second one, we do the opposite sign for the middle term. So a plus in the first one and a minus in the second one. So if I have to expand out 2a minus 5 all cubed, again, just like the perfect square, you might do a lot of this in your head, but be careful because there's a little bit more to think about here. So we start with the first term cubed. That's a minus 1, so we go minus first term squared, second term to the power of 1, and then plus, and then it's first term to the power of 1, second one squared, and then minus the last one cubed. So that pattern stays. And of course, remembering the coefficients of 1, 3, 3, and 1. So tidying that all up, that particular one becomes 8a cubed minus 60a squared plus 150a minus 125. Sum of two cubes. And again, you might not write that down, but you should be thinking, oh, okay, well, I know 8 is 2 cubed. So it will start with x plus 2, then it'll go x squared, but it'll be minus, because it's a different sign, and it'll be 2x plus 4. The biggest mistake here is to go minus 4x, because we're so used to writing twice the product, because of quadratics. But in this, it's not twice the product, it's just the product, a times b. Difference of two cubes, because of course 27 is 3 cubed. So I could think of this one as y cubed minus 3a all cubed. So we start with y minus 3a, first term squared, y squared, plus the product, so 3ay, and then plus the last one squared, so 3a all squared, 9a squared. In fact, when it comes to difference of two squares, difference of two cubes, there is a generalization for any power whatsoever. So you can have a to the power of n minus b to the power of n. It will always start with a minus b. And then there's that pattern again. Take 1 off the power of a each time. So every term, that power of a is going down by 1 until it is a to the power of 0, and we don't write it down. And the powers of b go up by 1. So it starts with b to the power of 0 and goes up. Any time, you can pick any term in that second one, and the two powers should add up to b n minus 1. So if I wanted to do x to the power of 5 minus y to the power of 5, it would start with x minus y. The powers of x will go down by 1. The powers of y will go up by 1. So we've got x to the 4, x cubed y, x squared, xy cubed, and y to the power of 4. This second one can also be factorised if you're patient enough, because it's true that any polynomial can be factorised down to a combination of quadratics and linear functions. It may involve complex numbers to get it down to linear functions, but using real numbers, we can always get down to at least quadratic factors. So any polynomial can be done that way. Now, we don't have a sum formula because the sum only works on odd numbers. That's why we don't have a sum of two squares, but we do have a formula for the sum of two cubes. So this one theoretically should be possible because 7 obviously being an odd number. The way I think of it is I still use this general formula, and I think of it as the difference, but it's -1 to the power of 7. And so that's the same as +1, because -1 to the power of 7 would be -1, and then terms the minus. So I can now use the formula up here. I just have to be very careful, because I'll start off with a minus -1, so it'll be a plus 1. The powers of a will go down by 1. The powers of 1, well, it doesn't really matter because 1 to the power of anything is 1. But what it has the effect of, you'll notice, is the signs will alternate. Because every time that -1 is to an even power, it'll become +1. And every time that -1 is to an odd power, it will be -1. And so whilst I haven't written them in here, the first term here would have been -1 to the power of 0, +1. -1 to the power of 1, -1, so that's why the overall thing is negative. Then it would have been -1 to the power of 2, +1, -1 to the power of 3, -1, and so on. And that explains the alternating of the signs for those ones. So as I say, this will only work when the powers are odd. So whilst I've written it down here as -1 to the power of 7, you don't really need to do that. Just remember, start off with the plus, and then the signs will alternate in the second one. That's all we really need to remember. Okay, exercise 1E has got some cubic questions and probably some more algebraic fractions as well in that one.